All right, kids. This is Mr. Martin, and I am generating this screencast for you. This is chapter 19. This is day one. It's going to be a minimum day today. Today's Thursday, and so this is the first day in our chapter 19 series. And I think you'll find it okay and understandable. And if you have any questions, please email me, and I'd be glad to respond to you. But here we go. We're going to take off and just get started. It's going to carry over from our gas laws in chapter 18. Remember, we had Boyle's law, which was pressure and volume, and then we also had Charles' law, which was temperature and volume. Now we're going to tie it all together with the number of moles, and we're going to also add a constant. And that's it. And then that's chapter 19. But here we go. Let's get started. All right. So there's a series of questions that I'm going to ask, and we'll answer along the way, and you can kind of think about it as we ask and answer them. What causes pressure in the container? And we've talked about this before. Last chapter where I blew up the balloon, we said what's causing the pressure, and the air molecules hitting the sides of the balloon are what cause the pressure. And the more that we add material, or in this case air, to the balloon, it was causing more pressure and more collisions hitting the side of the wall. And that's what it says here, the particles colliding with the walls of the container. And that's what causes pressure on any container. And then what could you do to increase the pressure? So first, what we did is we added more. Remember, and then we talked about Boyle's law. When we drop the volume, we increase the pressure. And so that was what we're referring to now. Just decrease the volume, increase the temperature, or add more particles. And that was it. So we added more particles by blowing the balloon up more, decrease the volume in those problems that we solved with using Boyle's law, and then increase the temperature. When we increase the temperature, we increase the volume, and there we go. We have this pressure. What unit do you use to measure large quantities of particles? And I'm going way back to the beginning of the school year when we talked about stoichiometry, and we're going to be using moles. And that's right, we talked about moles a long time ago, and we even had a mole day. Remember, October 26th from 6:02 a.m. to 6:02 p.m. 1 mole, if you remember, equals 6.02 times 10 to the 23rd particles. And that's it. A chemist doesn't. 6.02 times 10 to the 23rd. Please remember that. We're going to be using that quite often. So what happens to pressure as more particles are added to the system? And like we said before, if you add more particles, then pressure increases. There'll be more collisions, which will result in more pressure. So how are pressure and the number of particles related? And we did this in the lab. This was the part 4 of the lab that we just did last week. And this is when we added more particles to the balloon. And it says, how is it related? And it's a direct relationship. So as the number of particles increases, the pressure increases. Therefore, it's a direct relationship. So this is where we have the combined gas laws. And where do you think N? N is the number of moles, and that's what we're going to use moles for. N is the variable for it. So where should it go? Should it go in the numerator with pressure and volume, or should it go in the denominator with temperature? And we did this already, and we talked about it already, and this was on the part 4, like I said, and it goes in the denominator. It should go in the bottom, because N and P are direct. So anything that is direct goes in the denominator, and anything that is indirect will be together in the numerator. So here's what it looks like. PV over NT is equal to K. For PV, in other words, PV is equal to NKT. Now for K, K is a constant we use quite a bit in gas laws, but for this one here, we're going to use R. R is the new gas law constant. So it looks like this, PV equals nRT. And what we use to say that is Puvnert. So Puvnert is our ideal gas law equation. So it's PV is equal to nRT. P equals the pressure, V volume, N is the number of moles, R is our gas law constant, and T is temperature. And altogether, it's our ideal gas law equation. And we say Puvnert. So anytime you want to refer to the ideal gas law, we'll refer to it as Puvnert. So in this particular example, P, pressure, we're going to use kilopascals. And then we're going to use the number of particles in moles. That's what moles are going to be. Volume, decimeters cubed. When we're using gases, we talked about this, so especially when we're doing density, we use decimeters cubed. And temperature, you guessed it, always in Kelvin. Kelvin is what we're going to do. So anytime you're given Celsius, we'll convert to Kelvin. All right, so using Puvnert, or PV equals nRT, we're going to solve for R. So in other words, R equals what? There is a value that we're going to put in place for R, meaning that we have like a set value for R, and we're going to put all the other information in and solve for it. Now this is only relative to the units that you put in for pressure, for volume, and for temperature. So in this case here, we have kilopascals, decimeters cubed, and temperature will be in Kelvin. And of course, N is always going to be in moles. So that will be our units. So there it says right there. P kilopascals, V decimeters cubed, N moles, and T in Kelvin. So what are the units? Well, the units are kilopascals, decimeters cubed, mole, Kelvin. And so here's the actual value. It is 8.31. Now there's a number of values that are equal to R, but it only happens when they change the units. So on this one here, we're going to keep the units kilopascals, decimeters cubed per mole Kelvin, and that is 8.31. So we're going to keep that the same, 8.31 kilopascals, decimeters cubed, mole Kelvin. That is our R value, and that's called the ideal gas law constant. So molar volume, and when we solve for V, is the volume occupied by 1 mole of any gas at STP. Remember, STP is standard temperature and pressure, temperature being 273 Kelvin and pressure 101.3 kilopascals. So if we plug those in and use R, we're going to get a volume of 22.4 decimeters cubed. And you can try this in, and this is what we're going to do right now. We're going to solve for the molar volume. 1 mole is equal to 22.4 decimeters cubed. So here's what we do. So solve for V from Puvnert, and we get V is equal to nRT over P. So what we're going to do, and it doesn't matter what the gas is according to Avogadro's hypothesis, that's why it says 1 mole of any gas. So N is going to be 1 mole, R is going to be 8.31, T is going to be 273, and P is going to be 101.3. Looks like that. So you can see here that you have all these variables that we just plugged in. And this here, this 8.31, you're going to have to just take it for granted. This is what we've solved for. This R is given to us, and it is this value, 8.31 kilopascals, decimeters cubed, mole, Kelvin. It is the R constant, and it cancels out any units and gives us the unit that we want. So 1 mole is going to cancel out. Kelvin's going to cancel out here with 273 because that's standard temperature, and then kilopascal is going to cancel out here, which is standard pressure. And from there, if you do the math, 8.31 times 273 divided by 101.3 is going to give us 22.4 decimeters cubed. Believe it or not, that in itself is going to be a conversion factor. When we need to go from moles to volume or volume to moles, that's what we're going to use. So here's like an example. This is the ideal gas law example, and it gives you a pressure, 98.2, number of moles, 0.801, temperature, 20.8 degrees Celsius. So you know we have to change that to Kelvin. And there's R. R is 8.31. It says find volume. So all you're going to do is take this Puvnert, divide P out, and then solve for V. So V equals nRT divided by P, just like it was when we were solving for molar volume. So let's plug in everything that we have. It's just a substitution problem. But here's the deal. Here's the moles, R value, temperature 293.8. If you're wondering where did this come from, remember 20.8 is degrees Celsius. We must convert to Kelvin by adding 273. And when we add it, we get 293.8. And then 98.2 Kelvin, kilopascals, 98.2 kilopascals is the pressure given in the problem. And so it's just to pretty much just plug it in, substitute it in for all the unknown variables, solve for volume, you get 19.9 decimeters cubed. You're probably saying, wow, that's really easy, Mr. Martin. And it is that simple. We're just finding the variables to plug into Puvnert and getting some practice with it. So on this one here, here's number 1. And again, this would be a homework problem. It says what pressure, so that's P, will be exerted on 0.300 moles of gas contained in 8.00 decimeters cubed vessel at 18 degrees Celsius. You can see how everything is given in Celsius, so make sure you convert. So you would add 273 to 18. And it looks like this, it's 291 Kelvin. That's where the 18 goes. 18 plus 273 gives us 291 Kelvin. You plug it in. N is 0.3 moles, R is 8.31, and look how I have the units. There's a numerator and the denominator for R. And then T goes in the numerator, and then V goes in the denominator with moles and Kelvin. Everything cancels out. Kelvin cancels out, decimeters cubed cancel out, moles cancel out. I'm left with kilopascals. Let the units drive your problem. 90.7. There you go. So remember, King Henry David usually drinks chocolate milk. We're going to convert. If we convert 308 centimeters cubed to decimeters cubed, we talked about this other day. So remember, centimeters to decimeters is one shift to the left, but times 3 is 3 shifts to the left. 1, 2, 3. So it's 0.308 decimeters cubed if you ever need to convert that. So here it is problem number 2. It says how many moles of gas will occupy a 486 cubic centimeter flask at 10 degrees Celsius and 66.7 kilopascals of pressure. So in this one here, what's the question? That's what I'm always going to ask you is what is the question? And it says it right here in the first statement, how many moles? Remember, moles is N. So right here, if N is right in the middle, I'm going to divide both sides of this equation by RT. So N is going to equal PV over RT. Where's pressure? Pressure is 66.7 kilopascals. Volume, 486 centimeters cubed. Well, now we need it in decimeters cubed, so it's 0.486. 0.486 decimeters cubed. And then 10 degrees Celsius, well, we got to add 273, so that should be 283 Kelvin. And then R we know to be 8.31. So you plug it all in, and I want you to note right here, 8.31 kilopascals decimeters cubed over, mole Kelvin is over this here. You can switch the denominator, so if it's in the denominator, then the denominator becomes the numerator. You plug everything else in, and you end up with the number of moles. It's that simple because everything else is going to cancel out. And that's it. The downstairs becomes the upstairs. In other words, the denominator of 8.31 kilopascals decimeter cubed mole Kelvin, the mole Kelvin becomes the numerator. Here's your homework for tonight. Problems 1 through 3 on page 380 in the main text. And then the SPIC book, you'll have number 12 on page 108. There's A through D. And it says here for the SPIC book problems, you need to remember how to convert the number of moles to grams by using the periodic table. Look on the periodic table. Remember the units are grams per mole. And if you're given the number of moles, then moles times the molecular mass or the molar mass will give you the grams. That's problems 1 through 3. And this will all be due on Monday. I'm going to give you the rest of class time to work on it. All right, kids. Thank you. I'll see you soon.